Okay, hi folks. I'm John Regan. I'm from Maynooth University in Ireland, and I'm going to just fly through a little bit of a presentation on the emergence of massive black holes in the early universe and how LISCA can help to detect the mergers of these massive black holes and hopefully give us some clues as to how massive black holes are forming at high redshift and what the pathways to massive black hole formation are, which is, at the moment is currently unknown. Okay, so what did we do? So we had these high resolution ENSO simulations. These are adaptive mesh refinement simulations of the very early universe. Okay, so they're high resolution, so they weren't able to evolve down to redshift 0 or even 6 or anything. They only got to a redshift of 15, but it was the high resolution that was the key, that was the goal. So there's always a computational cost of these things. So we're trying to understand massive black hole formation high redshift. So you need this high resolution to really resolve the formation of the first galaxies and the stars in them, and hence the black holes within them as well. Okay, what did we find? So cutting to the chase, we found what we found I think was great. We found that there was a real mechanism for forming massive black holes or massive stars, if you like, in the early universe, and that mechanism was dynamical heating. So it's dynamical heating, this rapid merging of some halos in dense environments where they build up their mass very quickly. That suppresses early star formation, allows the halo to grow quite massive up to the atomic cooling limit, where it's cooled only by neutral hydrogen, and then you collapse through that cooling mechanism to form massive stars. You form more massive stars compared to normal star formation, let's say, because you've suppressed the initial stages of star formation. So you have more mass, a larger baryon reservoir, and a deeper potential well, and therefore higher accretion rates. So you form massive stars very naturally. So you don't need very strong radiation backgrounds, though you do need some mild radiation backgrounds. They're exactly what you'd expect at that redshift, and they're just formed by the local nearby star formation. So, and what we found was massive stars of up to about 6,000 or 7,000 solar masses, and of course that was just in one halo here. So I think what it's telling us is that we get star formation in the 10 to the 3, 10 to the 4, and possibly 10 to the 5 solar mass bracket very naturally, very early in the universe. Okay, so the Renaissance simulations, these were these high resolution simulations. They were in small boxes, relatively speaking. You can see the physical size here is of the refined region was only hundreds of kiloparsecs, so that's about 6 co-moving megaparsecs at this very high redshift. And we found 79 of these atomic coolers. So these are the ideal environments for forming massive stars. Okay. Also the number density, I just want to mention, is very high. It's much higher than the quasar number density. Okay. So what we had to do then is we wanted to go back and zoom in on some of these halos to see what was actually happening within them. So we selected 2 candidates. We selected based on the isothermal collapse. So ones in the parent simulation that were showing this perfect isothermal collapse. So they were staying hot effectively, which would be good for reducing fragmentation and driving supermassive star formation. For the zoom simulations, we needed very high resolution, like I said. So about what we got down to was around 10 to minus 3 parsecs. So the parent simulation had a resolution of about 1 parsec, so about 1,000 times more resolved. We dropped the dark matter resolution, or the particle resolution, down to 100 solar masses, and so that was about, 20 times lower than what the parent simulation had. The parent simulation was about 20,000 solar masses, so we dropped it down quite significantly. And we also included a prescription for supermassive star formation, so we could pick up the formation of these massive stars, and that's exactly what we see then. We saw that we formed these massive stars. Now they didn't actually fulfill the criteria for supermassive star formation all the way through their lifetime, so they did become ionizing sources. So they didn't, by that I mean that their accretion rates onto the stellar surface did not remain high, and that's because the stars move around. They move into low dense regions, and there's just simply no gas to accrete. Here's a little movie of that halo A, where you see these massive stars forming. The orange star is tracking the most massive star at any one time, but you can see there's a plethora of star formation going on, of massive star formation. These are the masses here. So it really is driving very massive star formation. Okay, we end up with something that's 6,000 solar masses at the end. And we ran these for After the formation of the first star, we ran them for an additional 2 mega years. Okay, so at that point you'd expect the first supernova to go off. So this was really tracking them in the pristine environment where they're metal free. But you can see the very high masses that you get up. And this was one halo, of course. Other halos in similar environments may generate more massive stars, and so that'll be something we'll be looking at. Or ones that have slight metal enrichment would be also very interesting to look at, because they should also drive massive star formation. But how does LISA tie in? Well, so what we did was using the very nice LISA sensitivity module by Robson, Cornish and Lube, which is available on GitHub, and it's their paper here. We use that code to generate sensitivity curves. So the blue line here is the sensitivity curve, of course, of LISA, what it'll be able to detect. And what we imagined was if we had two 5,000 solar mass black holes merging in one of these halos that I just showed on the last slide. So that seems quite reasonable, considering we were forming stars of 6,000 solar masses. So it's not unreasonable to assume that two 5,000 solar mass stars would merge together. It depends on the dynamics, of course. But nonetheless, what you see is that it's well within the LISA sensitivity range. So easily detectable, signal noise ratio of 32. If I go start that little movie on the right hand side again, you see here what you really want. This is signal to noise as a function of time to merger. What you want is you want to get up to a signal to noise ratio of, let's say, 10 or something like that, or between 5 and 10, and that happens actually around about 12 hours before the merger, and you'll see that in a second. So that tells us that it'll be in band for 12 hours, well detectable by LISA. So that's a good chunk of time there. And the difficulty, of course, will be determining the redshift. That will be challenging for these high redshift mergers. There's absolutely no doubt about that. And of course, we need the redshift to get the source mass. So that will be a challenge. So what are the conclusions? Conclusions are that simulations, and what I'm probably most excited and happiest about is simulations robustly predict the formation of heavy siege black holes at high redshift. So that's a huge bonus, or a huge boon, because that was a little bit unclear before, I think. So these simulations really robustly showed us this dynamical heating mechanism, this rapid merging or rapid assembly history of halos driving massive star formation. The number densities, I say, are somewhat uncertain, but we're working on that, but could be as high as 10 to the minus 4 per cubic megaparsec co-moving. That would be, of course, much higher than the quasar number density, but you'd expect that. We need better statistics, so more of this essentially, and we need more work on the dynamics, the merger rates, the backgrounds, redshift determinations, and so on required for the LISA modeling. But I think we're really in a good place and on a good track. Okay, thank you very much.